All right, so let's start. So we have been discussing about the shale gas, and so far we talked about why shale gas is different from other conventional oil and gas reserve. We also talked about its very low permeability and how with horizontal wells by means of creating hydrofracks, you enhance the permeability and you allow the shale gas to flow through the reservoir. We emphasized on that point that because this is an unconventional reservoir, we don't need the typical elements of a typical conventional reservoir like source rock, a reservoir rock, a cap trap, such combination. Uh, the same rock acts as the source, the same shell acts as the source, reservoir, and trap. Okay, we talked about some of its advantages. Okay, and let us look at some of the criticism that people have on shale gas. Okay, not everyone agrees with natural gas production from shell, and we will see why. What is their point? Uh, So, water agencies and citizens around shell regions are concerned about availability. So, say as I said, that you actually require a lot of area as an acreage while you try to produce shale gas, right? Because you need to drill a number of wells, right? So that essentially creates some sort of concerns among the citizens where you want to take the shale gas out, simply because availability of water supplies needed for gas production, because you will actually require a lot of water while you drill such wells. So that people think that perhaps that's a waste of water, of course. And then wastewater disposal also, when you produce such unconventional gases, you also produce a lot of wastewater. So these wastewater is generally contaminated with a lot of fines that comes along uh, with the water. Essentially, that's nothing but some remains of the hydrocarbon, some uh, rock chips itself and stuff. So it becomes fairly complicated how to dispose that amount of water, because both in coal bed methane and in shale gas you produce a lot of wastewater. Okay, so that becomes a concern. So there are cases of benzene contaminated in well water. Of course, as I said, it's not only the fines; it's also some of the aromatics that can contaminate your well water. Critics believe that hydraulic fracturing allows chemicals to leak into the groundwater. Sometimes these shale gas reservoirs are very shallow, and they kind of coexist with the aquifers from where we take out potable water, right? So people believe that there could be, I mean, there are criticisms around that if you frack a formation, if you create secondary fractures in the shell formation, what can happen that there could be a communication, there could be a kind of a pathway between the shale gas reservoir and your natural water aquifer, and that can contaminate your groundwater. So that is something also people criticize while shale gas ventures are proposed. Landowners in shale gas areas say the energy benefits are outweighed by the environmental risks. Okay, so that's always a thing for debate, when whether we need energy, whether we need and while you take that energy out, the amount of environmental impact that you do. So there must be a balance, and people think that because the size of shale gas operations are so large, that this is perhaps has more environmental impact than conventional oil and gas. So These are the places in the US, because US is the still the key player for shale gas. These are the places where shale gases are being explored and are produced from. Okay, this Marcellus shale is, this is, when you, very famous. I don't know if you have read in the newspaper about Marcellus shale or not. This is fairly big. You can see how large this gas field is. Yeah, it's pretty large, and people do debate about its. I mean, its environmental impact as well. So you can see US has still the kind of premier position in terms of shale gas production. Some of the other, important names are, for example, um, Baxter shale gas, that is very famous as well. Gammon, um, yeah, Woodford. Yeah, the most famous one is Marcellus. You can see the size of these fields. They're very large. So North America is currently the most profitable shale gas producer. Worldwide development of shale gas plays are expected to develop, especially in Europe and Asia. So now this is the world scenario. Now the brown colors essentially represents the assessed basins with resource estimate. So people have already been, kind of done a good amount of work and knows how much oil and gas is, how much shale gas is there. Then the pink one are the assessed basins without any estimate. Uh, then the white ones are the countries within scope of report, and then countries without scope of report. I mean, they don't have much. I mean, they did not invest a lot on shale gas. Now, if you look at India, of course, um, yeah. So in this brown color essentially represents your Bombay High, and rest of it is still yellow, and then you can see a small sliver here as well. That is my Gondwana basin. Okay, so there people have actually, these are the two areas. This is Bombay High, uh, and this is Gondwana basin. Okay, these are the two places essentially where people are have explored it quite a bit, and have given an estimate of how much shale gas is present now. Okay, now because US is something, is like a key player, so we need to know some of these statistics. By the end of 2008, shale gas production in the US was up to 31.8 trillion cubic feet. Okay, the US contains an estimated of 5,000 trillion cubic feet of shale gas. Only 500 trillion cubic feet is recoverable. Okay, so this is the total keep, and this is the UR. And you can see that there is a large difference, right? I mean, you can only take out 10% of it, right? So this very less, 10% ultimate recovery factor. Why 10% recovery factor? Why this is very low? Because of low permeability, okay? So although the GIP is very high, you can see that the recovery factor is fairly low. It's in the order of 10%. It is estimated that shale gas in the US is enough to meet United States gas needs for next 90 years. So think about it. I mean, we can only, from the US, if we take it as an example, only 10% of it, can sustain the energy needs for next 90 years. So with research, if you can essentially improve this recovery factor, okay, Of course, you can have more years with sustainable you know supply of gas, right? So one of the research that goes on the shale gas front is essentially improving this recovery factor. That is fairly important. So it's a very difficult to obtain gas. Of course, as I said, each shale gas basin is different, and it has its each set of unique operational challenges. Because of these differences, the development of shale gas resources in each of these areas faces potentially unique opportunities and challenges, of course. Okay. So, also we know less about such because conventional oil and gas we have been producing for 100 almost 100 years, right? So we already know a lot about how to produce them, how to overcome difficulties and stuff. But shale gas is fairly new, right? So it brings opportunities in terms of research, and of course it brings also challenges in terms of the unknowingness. Okay. So the environmental problems could be, protection of groundwater, as we have talked about, wildlife impact, simply because you look at the huge area of the Marcellus shell field, so it actually the land use is very very large. Okay, large land use. So if you have large land use, of course you that will essentially lead to deforestation, right? Because the land will not come from the sky. You have to create your own land. So that means that will require deforestation. So if you do deforestation, of course, it is going to impact the wildlife. Community impacts, deforestation, and you are completely changing the landscape of a particular area. So that, of course, means the community will be impacted, and surface disturbances, of course, that is accompanied with such hazards. So, what are the groundwater issues? Chemicals are added to water to aid the fracturing in the rock. We talked about it that simple water has a density which is very low, so 1 gram per cc. So that is not good enough always to actually overcome the minimum horizontal stress of the rock and frack it. So what we have to do, we have to keep on adding, for example, mud into your water that will essentially thicken the water and increase the density. And hence, we will be able to impart more pressure on the formation and fracturing will happen, right? So, but if you add such chemicals into water and if that water essentially leaks to something else, maybe in potable water, that is not good. So that is the first point. The water is stored in above ground ponds until it can be removed or injected back into the earth. Okay. So what is generally done? Both the water that is going to be used for fracking, as well as the byproduct water that comes out after drilling. That is generally stored in big ponds. Big ground ponds, and there are also instances where such ponds get leaks and then it contaminates the uh, the aquifer. So to overcome that, people talk about reduce, reuse, and recycle. Okay. In using the technique, researchers are trying to find ways to cut down the water pollution. It takes 2 million to 4 million gallons of water to drill and fracture a horizontal shale gas well. Okay, so you can see how large the amount of water that is necessary. Okay, and this all this water is going to get contaminated. So of course the best way to actually do this in a sustainable way is to practice this technique of reduce, reuse, and recycle. So in the long run, is not bad compared to the agricultural and municipal use. Only 0.1 to 0.8% of the total water use. Okay, so what they are essentially saying that, if you, in those ponds that we just talked about, if you keep them for a long period of time, by natural filtering, all the contaminant in the water actually moves away, and then you can use them for agricultural and municipal purposes. So, water treatment techniques. Current techniques are like underground injection, treatment and discharge, and recycling. And new techniques that are developing, and where, the environmentalists, the ones who, for example, once amongst you who wants to work in the water pollution, as far as the environmental science is concerned, these are the areas, new areas for research. So researchers want to use this water to be clean enough to be used for other purposes as well. So you have to find out ways to essentially clean that water. I mean, clean it to such extent maybe it can be used as potable water as well. As way this way, shale gas and associated water can be considered as a resource of its own. Okay, so the water that you produce, the water that you essentially the water that gets contaminated, if you can find a way to actually get rid of the contaminant, that can be used as a resource too. So you can see here a beautiful picture. You can see there is a shale gas well which is being drilled here. Yeah. So you see here the color of the water. This is pretty fresh, right? So from this water goes through this pipe, okay, and is fed through the well to drill the well, right? And then this is the water that comes out. This is another pond where the water is stored, and you can see, of course, the color of the water is almost yellow. Okay, so that has happened simply because it has got mixed with a lot of contaminants while that well has been drilled. And the other thing that you can see here, of course, while this drilling site has been made, a lot of deforestation has been done as well, right? So that, of course, will create environmental impact. Now, remember, this is not one, two, or 20 wells. These are like thousands of wells that you drill in an area. Maybe you can see another well site here. So in a short gap, you drill a number of wells because you need to drill such number of wells because of the low permeability of the reservoir. You need multiple number of wells. Hence you need a hence the area that you impact on the surface is also large. So gas development can adversely affect animal habitat and wildlife that we have just discussed. They can drill underneath sensitive areas like wetlands and reduce wildlife disturbances. So that can be a solution to that problem. Okay, community impacts, damage of roads, traffic congestion, traffic flow, noise, dust. I don't need to spell it out for you. You can understand any industrial operations can have such impacts. It takes intense planning to ensure these factors have smallest impact as possible. Okay, so good planning is the key. So, what are the benefits? We talked about a lot about its concerns and what critics actually say. Natural gas is the cleanest fossil fuel. So that is the first thing. The if you can take out the gas when you burn it, it emits minimum amount of carbon dioxide. So that is the very big advantage. What is the second advantage? The main products of natural gas combustion are carbon dioxide and water vapor. It doesn't produce really a lot of carbon monoxide. Okay. Okay. So we actually, there are more toxic gases. Say for example, if you burn, for example, oil actually contains lead as well. So that is far more dangerous than carbon dioxide in the right perspective. Okay? So if you burn gas, methane, This is simply methane. What happens? You essentially only emit carbon dioxide, and we now know about different processes by which carbon dioxide can be minimized, and people have worked a lot. So carbon dioxide, although it's fairly dangerous in terms of global warming and greenhouse effect and all, but this is not the most dangerous gas. Okay, say for example, if you in oil as well, you can create sulfur dioxide or H2S. These are far more dangerous gases than carbon dioxide. Okay, so but natural gas has its original advantage that if you just burn it, what you will create only carbon dioxide and water vapor. Okay, they are dangerous in terms of greenhouse gas, being greenhouse gases, but then they are also not as dangerous as some other gases. So in that way, it's not that bad. So natural gas doesn't contribute to smoke. Smokes are generally contributed by, the particulate matter, the aerosols. If you burn gas, you don't create aerosols, okay? But if you burn coal, you do create fumes, aerosols, right? So it's a natural advantage. Can be used to fuel vehicles directly. You know? So the social spectrum pros, it creates a lot of jobs, less pollution. There are money to be had. I mean, it's really good business. May cause lower prices for fuel in future. We talked about this. After the shale gas revolution in the US, of course, the gas price dropped drastically. What are the cons? There are many development issues when it comes to shale gas. We said that they're very unique because we are still learning. People don't necessarily want their land to be dug up, because it takes a lot of land use and land cover. So it essentially, of course, say for example, tomorrow I find out that you know this whole Bhopal has a very beautiful shale gas reserve. I mean, it will be very difficult to convince the resident of Bhopal to move to someplace else so that I want to drill wells here. And that's not one or two wells, 1,000 wells in Bhopal. That will be very difficult thing to sell to people, right? So yeah, so because you cut a because of the land use, there is also cons in terms of the wildlife problem. So, of course, what are the political spectrum if we think about? So, pros: greater energy security, more money to be had by local and state governments, allows less dependence on foreign oil. Yeah, that is, shale gas actually now is developed in America. Okay, so that was one of the inspiration for developing shale gas in the Americas. What are the cons in developing shale gas? There are a lot of factors that needs to be taken into consideration. Yeah, of course. Yeah, paperwork that is there everywhere. So economic issues, advances in hydraulic fracturing and horizontal completions. Costs, I mean, hydraulic fracturing and horizontal completion is not as straightforward and as cheap as a vertical well. A vertical well is cheaper, you know, and the completion is also cheaper if you don't have to do hydraulic fracturing. But if you have to do hydraulic fracturing in horizontal completion, it's of course expensive. Costs more to produce, but low risk shale gas wells. They are but the well cost is fairly high, but they are low risk because you don't generally drill a very deep shale gas well. North America is development leaders. It actually creates a lots of jobs and boosts up the economy. Skip this one. Okay, so that's all I wanted to talk about shale gas. It was not a very, I mean, the technicality is fairly simple. It's a um, it's a low permeability reservoir. The source the reservoir, the trap is the same rock itself, and that happens simply because it is low permeability. You generally drill it with horizontal wells, and then you have to frack the formation to take hydrocarbon out. And because it's unconventional, there are some advantages and disadvantages associated with it. The major disadvantage, not only for shale gas but also for any other unconventional resource, is the water treatment. You really need a lot of water to drill the well. Also, the recycled water is also large in volume. Okay, so to manage that water is an area of environmental research. I mean, people are really all around the world. People are working a lot around solving the water problem for both coal bed methane and shale gas. Do you have any question? Anyone? If not, then I will move to any another topic quickly. Any questions so far on shale gas? Easy. Okay. The next unconventional reservoir we are going to talk about is tight gas. Now, what is tight gas? Tight gas is also low permeability. Tight gas is also low permeability reservoir. Okay, it's also low permeability reservoir. But the difference with tight gas and shale gas is here the reservoir is primarily sandstone. Okay, here it is not shell. Okay, so the uniqueness is these are reservoirs with sandstone reservoirs with extremely low permeability. Sandstone reservoirs are with extremely low permeability. So we'll discuss what it is. So now this is a very interesting diagram, and you can actually it's a very thought-provoking diagram as well. Now what you see here, that at the bottom of the pyramid there are these three unconventional gases are put: coal bed methane, shale gas, tight gas, and then you of course have and then of course in this axis you can see that the permeability decreases towards the bottom. So the matrix permeability of coal bed and shale gas is fairly low, in the order of 10 to the power minus 4 millidarcies. And for coal bed methane, it is the reservoir is coal bed. For shale gas, the reservoir is shell. The for the tight gas, it's not shell, it's sandstone. Okay, and it's like 10 to the power minus 3 millidarcies. Okay, 10 to the power minus 3 to um, you know mm, 0.1 millidarcies. That is where the tight gas permeability um, essentially sits around. Okay. And then if it is more than 0.1 millidarcy permeability, we regard that sandstone reservoir to be a medium quality sandstone reservoir, conventional. Okay. And then if it is more than 1000 millidarcy, it's a good quality sandstone reservoir. Now, what you are observing, the interesting thing is that these tight gas, shale gas, coal bed methane, they are very difficult to actually take out of the ground because of very low permeability, right? But they are very large in volume. But as that permeability actually increases and uh, the resource become more permeable and easy to extract, you can see for the high quality conventional reserve, you know, the volumes are considerably small. Okay? So, what is the scenario right now in the world? That we have kind of, got rid of all the high quality reservoirs. They are empty. We have explored and produced significant amount of medium quality reservoir as well. Okay. Now we are actually left with a very large volume. That is true. I mean, because as you have seen that for shale gas, the example that we have given for US, with only 10% recovery factor, we can take out. I mean, with almost 90 years of US's economy can be supported by only 10% of shale gas. I mean, can you imagine that if you think about it, right? So the volume is not the problem. There is plenty of it is left in terms of these unconventional reservoir, tight gas, shale gas, and coal bed methane. But the issue essentially comes how to take them out, because they're ultra low permeability. So with increasing demand, of course, we have no choice but to actually uh, produce from them. Okay. So we need better technology, of course, and then confine drilling and development. Okay, because nowadays it's continue with drilling and development. So we need to have better technology to do that. So this provides you a rough estimate of the reserve for worldwide for coal bed methane, shale gas, and tight gas. That accounts for the large amount of the unconventional gases. Okay. You can see in North America, that is where it is the highest. Coal bed methane around 3,000 TCF. Shale gas is around 3,840 TCF. Tight gas, tight sand gas, because they have to be sandstone reservoir, around 1,371 TCF, in total 8,000 TCF. Okay. Let's see if we have India here. Perhaps it will not have India, but let's see. Asia and China. Okay, so that includes, and Pacific. That means that will include Australia as well. Okay, significantly lower than what we have in the North Americas. Okay. Okay, we have to include this one as well because this is the other Asia Pacific in Southeast Asia. So that's the scenario. So tight gas characteristics, very low permeability, less than zero point 0.1 millidarcy. You need frac job and horizontal wells like shale gas. Okay. Large pressure gradients across reservoir. Okay. This is an interesting thing to understand because let me just go back. I was not being able to see if I can. Perhaps I was not. I have not enabled the editing, hence I was not. Just a moment. Give me one moment. Right. So this is an important point to understand. Large pressure gradients across reservoir. Why would there be large pressure gradient across reservoir? Suppose this is a tight gas reservoir and this is a conventional reservoir. Okay. So tight gas means so you can imagine that it's almost very fine grained sandstone because grain size essentially larger the grain size the permeability actually increases, right? So very fine grained sandstone creates this tight gas reservoir. Okay. Now, of course, in case of a conventional reservoir, I have fairly large grains and good permeability. That means the flow, the fluid can flow easily to the pond, to the space. Okay. Now, for example, I have drilled a well here and producing hydrocarbon, okay, gas. Because of the so if I produce gas from here, what will happen? Suppose the reservoir pressure was P1 in the beginning, okay, and then because I am producing gas, I will slowly deplete the reservoir. The pressure will keep on decreasing, and we will observe that the you know so the low pressure zone will slowly start to increase. So it will still remain P1 here, and this will become P2. And it will take a long time for P1 and P2 to equilibrate because the permeability is extremely low. But if we compare that in terms of a conventional reservoir, here I am making P2 by means of taking the oil and gas out, you know, and here is P1, my virgin pressure of the fluid. It will take less time to equilibrate because there is high permeability. So the fluid can flow easily. Hence, it will be equilibrated very smoothly. Okay, in a much lesser time than a tight gas. So that's why they say that there's a large pressure gradients across reservoir while you start producing them. Okay. So high transient decline rates. I will explain that in a moment. But this is very related to what I have just discussed. I'll explain that. Often commingled production. Uh, Commingled production means this will, uh, often what happens that you in the tight gas also you have some leftover oils, and it becomes very difficult because of very low permeability. There is not a very fixed free water level. Okay. So what I mean by that, for example, in a conventional oil and gas, I have a very fixed, for example, GOC, gas oil contact, right? So if I drill here, I will only produce gas. But if I drill up to this and then perforate here, okay, I will produce oil. But then such boundary is often not very well demarcated in case of oil tight gas. Okay. So there is a chance of commingling of production, often layered and complex. I'll explain this one as well. These 2 points I will explain in a moment. High transient decline rates and layered and complex. So this is the total unconventional scenario in the whole world, if you like. So the brown color represents shale gas, the green color represents tight gas, and the blue color, sky blue color, represents coal bed methane. Okay. You can see how they are distributed. If we look at India, okay, what do I see here? I can see the presence of shale gas and coal bed methane. Okay. You can observe this Gondwana basin, which has both in Gondwana basin, which actually starts from MP itself. All the way to West Bengal. So these Raniganj coalfield, Jharia, Bokaro, all these belong to the Gondwana basin. Okay. So they have prospectivity both in terms of shale gas and coal bed methane. So high resolution layered sand. Okay. So for these coal bed, for the tight gas, generally another type of well logging is essentially uh, looked into, which we called as NMR. magnetic resonance, natural magnetic resonance hubs, well logs, okay, and they help you to detect very thin sand layers, okay, very thin sand layers, which you cannot detect with gamma ray, okay, and the layering in them, okay. So that is crucial in case of tight gas production. So this is an example, of course, okay. Net pay using high resolution 50 feet, okay, high resolution NMR logs, essentially, which will be the reservoir rock for shale gas. So another very important log that is necessary for shale gas, coal bed methane, as well as your tight gas are your image logs. Because I hope you have seen the video of or the presentation by one of the groups who created presentation on image log, and they will tell you more that these are the natural beds, dipping beds, and these are the others are actually the fractures. These are fractures. So it's a naturally fractured reservoir. So if your tight gas reservoir or a shale gas reservoir is inherently fractured, it's always already has natural fractures, that is always good because they provide you secondary permeability. So what you can do, I mean, maybe you need less fracking to enhance the permeability because of these naturally occurring fractures, your low permeability is little more. I mean, the permeability is not as low as it should. Because of the presence of such naturally occurring fractures. So this is a beautiful representations of such natural fractures. You can see a picture of a natural fracture. These are the natural fractures. So from these image logs, you can actually identify the strike and the dip of these natural fractures, which is plotted in this rose diagram. And this is another type of log, which is called dip metered log. Okay, that provides you the tip of a formation. Okay, so generally you find these green dots, as you can see here. These green dots, they represents the presence of bed because they are low dipping, and these blue dots are the dips of the fractures because the fractures are generally at high angle with the beds. Okay, so with a dip meter log and together with an image log, you can actually identify the naturally occurring fractures in a shale gas, tight gas, and a coal bed methane reservoir. So this is what I was talking about. Let's see, uh, you know, so the drainage area, and I was talking about it. I just gave you a uh, gave you a brief understanding of it. So what you can see here that this first batch of picture actually shows you the pressure depletion. Okay, pressure depletion after 1 year of production. Pressure depletion after 1 year of production. This first one, two, three, four pictures, and then this is after 10 years of production. Okay? So hotter the color, I mean the red color means it's almost virgin pressure, and blue color means the pressure has been depleted significantly. Okay, and it follows the rainbow scheme. Okay. So now you can see this is zero point 0.1 millidarcy reservoir. This is 0.01 millidarcy reservoir. This is 0.001 millidarcy reservoir. And this is 0.0001 10 to the power minus 4 millidarcy reservoir. Okay. And this is suppose this is my horizontal well. This line is my horizontal well. So you can see in a high permeability reservoir. Okay. Now, when you start after 1 year, say for example, everything was red. After 1 year, you can see everything has become yellow. So there is a very good pressure communication. Okay, and after 10 years, you can see everything has become blue because I have excellent pressure communication. So the drainage area of the well is large. That means it is draining hydrocarbon from a larger area. Okay, and then as my permeability is decreasing, I can see my drainage area is keeping on decreasing. And for something which is 0.001 millidarcy, point 10 to the power minus 4 millidarcy, you can see how small the drainage area is after 1 year. And that has not significantly changed after 10 years as well. So we have only drained from this amount of area. So after 1 year, this is the amount of the area we have drained from this horizontal well. And after 10 years, I have just drilled from this. Okay? And rest is still P1, still virgin pressure. Okay, so that's why if I want to drain this whole reservoir, I will need more wells because otherwise I have to. If I have less number of wells, what I have to do, I have to maybe produce for infinite amount of time. But that is not something is practical, right? I have to drain the reservoir as fast as possible. I mean, reasonably as fast as possible. So because the drainage area is gets significantly lower with the decrease in permeability, I will need more wells to drain the same reservoir with less permeability. Okay? I hope this point was clear with you. Okay. So, you can see what you can see essentially. So, this is a conventional reservoir response. So, what I am seeing, this is the initial pressure, and this is with time. So, you can say this is initial pressure. Forget about PZI. That's difficult to understand for you at this moment. But remember, this is the initial pressure, and this is how the pressure is depleting. Okay, you can see a very beautiful, linear decrease of the pressure with production. Okay, so this is time. Okay. Now, for tight gas, because it is low permeability, the pressure is kind of sluggish. The response is sluggish. It's not as beautiful as a conventional um, reservoir. Okay, so that is what I meant by declined. You know, high transient in decline rates, and because it is extremely low permeability as well. You know, the whole reservoir is not drained together, so it comes. The response is like more than one layers. Like if you see here, you will see. Yeah. As if I mean I have one as if one layer is here. Oh, I'm sorry. As if one layer in the PZ plot, one layer is here, then another layer is here. As if they're behaving as a layered complex. Okay. So just to summarize, I think we have talked all about it. You know, yeah. So it's a very low permeability reservoir. Okay, and the drainage is essentially very low. The drainage area for a particular well is extremely low. So you need to also frac a tight gas reservoir, and then you know drill a horizontal well to take the gas out of it. Okay. Is there any question? Anyone having any question? All right. If not, then I will see you on Friday. So Friday we have the talk from an external guest. Please be there. And I will start talking about coal from from next week. And next week also there will be a quiz. Okay. So I will let you know about the date, and you will have enough time to respond to your quiz. So please start preparing. So everything that I have taught on petroleum geology will is included in your quiz syllabus. And next week we will have a quiz. And yeah, thank you very much. I will let you know about the dates
Hello,
of.
sir.
Yeah.
Sir, sir, actually, like the fifth years will be traveling back to college next week, sir, from between 4th to 7th.
Okay. So we will not have it between 4th to 7th. We will have it between
Yes, sir. That.
some 3rd, 8th. Okay.
Yes, sir. That is okay. Yes, sir. Thank you, sir.
That's fine. Okay. All right then. Okay. Thank you.